Good morning, ladies and gentlemen, boys, girls, fellow Homo sapiens. I had a question that said, please, could you do a diffraction problem so I can see how it works? So I'm looking at page 538, practice B, number 1. Okay, what we're expected to do is we have a diffraction grating with 5.000 times 10 to the third lines per centimeter. That is used to examine the sodium spectrum. Calculate the angular separation between the two closely spaced lines of yellow in sodium at 588.995 nanometers and 589.592 nanometers in each of the first 3 orders. Okay, interpretation. Okay, lines per centimeter is not quite the distance. 1 over that, because we want a length, is my distance between the slits we're looking at. So when we do this, we're going to have to change lines per centimeter to meters because that's our standard answer. When we solve this math, we get 2.000 times 10 to the negative 6 meters. That's just showing we have 4 sig figs. Lambda 1. Given in nanometers, we need to change that to regular meters. Well, there are 10 to the 9 nanometers per meter. Changing that gives me 5.88995 times 10 to the minus 7 meters. Again, this one has 6 sig figs. Same thing with lambda 2. So these are the 2 different yellow lines in sodium. If you ever look through a spectroscope at sodium, you're going to see a bright, depending on how good your spectroscope is, you're going to see a bright yellow line in the middle, which if you've got a good enough resolution on your spectroscope will actually show up as 2 lines right in the middle. We want to find the angle for each one of these. So again, we run it through the diffraction grating. We're just going to say these are the 2 slits here on our screen at 0, which would be perpendicular and centered on the slit. You're going to see a bright spot there. You're going to see at each location the next bright spot. This would be at m equals 1. This would be at m equals negative 1. M equals 2, m equals 3. And then that will happen for each color, each frequency. Now, at m equals 0, they should all be right there. M equals 1, we're going to say they're going to be slightly different. M equals 2, they're going to be slightly but probably more different. Well, they will be more different. And then m equals 3, they're even going to be farther. We're looking for this angular separation here. So how far these 2 are from an angular difference there. That's what we're looking at. Hopefully that makes some sense to you. I suppose I could draw that out. So if this is the center line, these are the slits. So there's my center line. I have this is my angular difference. This is what I'm looking at here. So as I go through, I'm going to solve this for each one. So I'm going to find m equals 1, 2, and 3 for each one of these. I'm going to find the angle. And then I'm simply going to take the difference of that angle. And since I'm only looking at the difference, I don't care whether it's positive or negative. I just put the absolute value signs around delta, theta here. And we're going to solve for m equals 1, 2, and 3. Well, we look at our simple formula. What do we have? We have, to stop dropping our papers around, we have that d sine theta equals plus or minus m lambda. Now, since we're only worried about the positive in this case, we're going to keep it consistent. I'm just going to get rid of that for the moment. I'm looking for theta, so I get sine theta equals m lambda over d. Therefore, theta must simply equal the inverse sine, sometimes known as the arc sine, of m lambda over d. That's what we're looking at. So there's the formula I'm going to simply repeat. So we're going to do that for theta 1 and, lambda 1 and lambda 2. So plugging in for m equals 1, I'm going to have that theta here must equal the inverse sine. Well, m is 1, so I'm going to drop that, and this is going to be 5.88995 times 10 to the negative 7 divided by 2.000 times 10 to the negative 6. M equals 2. Theta for this will simply be sine negative 1, 2 times 5.88995 times 10 to the negative 7, all over 2.000 times 10 to the negative 6. And then m equals 3. Theta will simply equal the inverse sine of 3 times 5.88995 times 10 to the negative 7, all over 2.000 times 10 to the negative 6. For theta 2, it's the same thing. So we would have, in this case, theta would simply equal the sine of negative inverse sine of lambda 2 over d. Same thing, except now this one is simply theta must equal the inverse sine of 2 times lambda 2 over d. And this one, theta, must simply equal the sine of 3 times lambda 2 over d. Inverse sine there. Going down and solving. Putting in numbers, hopefully, for here for lambda 1. First one, I get 17.127. Good to 4 sig figs, so I just stopped. Over here, we get 17.145 degrees. Delta theta for these two guys then is 0.017. And again, this is only good to the hundredths place. 0.017897, which rounds to 0.02 to 2 sig figs. Okay, so that was m equals 1. M equals 2. 36.0857, 36.12806. The difference between those then, I ended up getting, so delta theta turned out to be 0.042, again, only good to 2 sig figs, 3, 3, etc. So this was 0.04 degrees. Then my last one, 62.00066, sorry, you're correct there, 57. And this was 62.1763, again, good to 4 sig figs. When I subtract those, I ended up with 0.11 degree. So my answer for this problem should be at theta 1, m equals 1, we had delta theta was 0.02 degrees. For m equals 2, delta theta was equal to 0.04 degrees. M equals 3, delta theta was equal to 0.11 degree. Hopefully that was what you wanted. If not, remember, just email me if you have questions. See what I can do for you.